Yes.
All right, sure then. Okay, good afternoon, everyone. I'm Kyaw, and my paper is titled Personalized Federated Learning, a Combinational Approach. First, we should start off with the motivation and the overview of the paper. This section will address three overarching questions. What is federated learning? What is personalized federated learning? And why a combinational approach for it is explored in this paper. In recent years, the rising popularity of edge devices, such as mobile phones and wearable devices, has led to the rapid growth of private data originating from distributed sources. The wealth of such data offers vast opportunities for machine learning applications in various domains. At the same time, modern society is becoming increasingly concerned about data privacy, with the introduction of legislations such as the GDPR, the General Data Protection Regulation, which seeks to regulate how data can be stored, transported, and be used by corporations and institutions. Naturally, since data is needed to train machine learning models, machine learning is affected by them as well. More of such regulations, perhaps even more stringent ones, are bound to arrive in the years to come as governance catches up with technology. We are also beginning to ask ourselves important questions, such as whether a world with AI but no data privacy is really a better world, and whether we are willing to trade data privacy off for some semblance of progress in machine learning. But when we look at the most prevalent machine learning systems today, the design is one of centralized data aggregation. Data is stored in a single location and is used to train a model, and that model is then deployed for everyone to use. This does not play well with the aforementioned regulations and the regulations that are bound to come. Individuals will also be reluctant to knowingly share the private data of themselves that will be stored in some unknown server halfway across the world and be used for unknown purposes or even possibly against them for profit. For example, Apple recently released a feature for users to restrict the collection and tracking of personal data by apps. And in the first week alone, more than 70% of users have opted to do so. And this just goes to show how data privacy is increasingly becoming a pertinent and important issue to address for the future of machine learning. But what if we could have the best of both worlds, having both data privacy and machine learning? That is what federated learning is about. And because of this, federated learning has grown in popularity over the past few years. And it is a learning paradigm that enables the development of a joint machine learning model on silos of data in a collaborative yet privacy-preserving manner. And in FL, each person or device or organization that wants to train and use a model is referred to as a client. And the key motivation for individual clients to participate in FL is to leverage the shared pool of knowledge from other clients in the federation. And the individual clients often face data constraints such as data scarcity, low data quality, and unseen classes that limits their capacity to train good performing local models. And a local model here refers to a model that is trained only on the individual client's data. And FL will theoretically fix all of these issues about having little data by giving them access to the whole pool of knowledge from other clients while still maintaining the data privacy issues. And so FL can be further classified into two scenarios, cross-device FL and cross-silo FL, with the difference between them being the number of clients, with cross-silo FL having a significantly fewer number of clients, but with a lot more data per client. An example of a real-world usage of cross-silo FL is NVIDIA's Clara system, which is a FL system for healthcare. Recently, during the pandemic, it was used to predict which hospitals will be overwhelmed using private healthcare data from different institutions, hospitals, and clinics, and this helped to preemptively deliver oxygen to those hospitals to prevent an oxygen shortage. As for cross-device FL, the predictive keyboards on our smartphones are prime examples of FL, whereby it is used for our network prediction task. The prevailing FL setting assumes a federation of clients, which is why it's called a federated learning. And, and these clients are basically like mobile devices or organizations, and they collaboratively train a model under the orchestration of a central parameter server. And the training data is stored locally on the client side, and it is not shared at all during the training process, unlike the machine learning systems that we have today. Most of the existing methods for training for federated learning are variants of the original algorithm called federated averaging. And this is what we focus on in our paper as well. The goal is to train a global model that performs well on most FL clients. How exactly federated learning happens? can be distilled into these few steps. First, the central server randomly initializes a global model, which is then distributed to all clients. The clients then locally train the model using their own data. And instead of sharing the data, we will just send back the updated model weights to the server. And the server that averages these updates into an updated global model, which is then distributed once again to all of the clients. And surprisingly, this works and helps to improve the model over iterations. And compared to local training, the globally shared model, trained through the federated learning process, generalizes well to unseen data, as it is trained on large amounts and a large variety of data. However, being a generalized model, they are designed to fit the average client. And this is where the problems start. And this means that they might not perform well in the presence of statistical data heterogeneity, such as in the case whereby the local data distribution of one client deviates significantly from the global data distribution. And this is what we will term as non-independently or identically distributed data. Enabling federated learning to deal with such data is important because of the non-independently and identically distributed nature of data that originate from the real world, since real-world clients should not be expected to have the exact same methods of data acquisition or environments or like circumstances. And FL also faces issues about privacy, whereby FL models can leak data. And to counteract this, differential privacy, TP, is commonly used. FL models are also vulnerable to adversarial attacks, like data poisoning, and robust aggregation, RA, has been commonly suggested as a possible remedy against such attacks. However, while these two additions will provide these safeguards, they also degrade the FL model's performance. And such losses in performance will disincentivize clients from participating in FL, since there might not even be a significant or a positive performance gain at the end of the day. One way to overcome this performance decline is to actually use personalized federated learning. And this is simply an intermediate paradigm between the server-based FL paradigm that produces a single FL model and the local model training paradigm that most machine learning systems are using. And the challenge is to strike a careful balance between the local task-specific knowledge and the shared knowledge that is useful for generalization. And there are several approaches for personalization that has been explored in previous works. And in this paper, we will focus on the ones that happen after the FL training process and not during. These existing approaches have been shown to yield positive net gains in performance, but for their specific test data sets and for their specific task. However, no work has been done to combine these approaches together, which could provide even further gains in performance, but only if the right combination is used, which are all compatible with one another. And so, in this project, we address this gap and evaluate various combinations of personalization approaches in the scenarios of plain FL, federated learning with differential privacy, and finally, one with robust aggregation. Now we move over to the experimental setup that we have, and here we will be talking about the data sets, tasks, and approaches that we used. So this is the overview of the experiments that we conducted and the variables changed. We differentiated the setups by the FL scenario, the tasks used, and the data sets used. The tasks that we performed were essentially image classification, text classification, and next word prediction. These tasks actually have real-life applications for federated learning, such as the predictive keywords for next word prediction. For the image datasets for image classification, we have 3 datasets with different number of clients. FIFA10 is repurposed into the cross-domain FL dataset with 100 clients. And basically, for each client, images are randomly distributed in a non-independently and identically distributed manner. And for the domain net and office datasets, they are essentially cross-silo datasets with 5 and 3 clients respectively. Each client comprises of a single type of image. Like for instance, for the sketch client, it will be pretty much sketches of images, where basically they are objects and they are sketches of them. And as for the webcam client, which you will see for the office data set, these are essentially images taken with a webcam. And task is for image classification. And this is similar to the kind of statistical heterogeneity that federated learning systems will face in the real world, where the data across clients is quite different, but still share some similar qualities. As for the text datasets, we have 2 kinds of datasets, the comments datasets and the review datasets. The comment dataset is made up of comments from Reddit by 80,000 users over a period of a month, and it is used to train the next bot prediction model. The reviews dataset is used for tag classification and are made up of reviews. So for the cross-sector datasets for these reviews, each client corresponds to a particular sector or particular product category. Like for instance, for cross-sector, it can be from hotels or restaurants or consumer products. And for the cross-product dataset, it is essentially product reviews from different categories like electronics or specifically phones or headphones. And the objective is to classify the reviews from 1 star to 5 stars. As for the personalization approaches, we explored 5 of them. We chose these 5 as they tend to be the more popularly used ones, and they also tend to be easier to implement. The first one is fine-tuning, which is to take the final FL model and train it for a couple more epochs on the local data of the client. And this happens for each client. A modification of this would be freeze-based fine-tuning, which is to freeze all of the layers of the FL model, except for the final few layers and the training on the local data. Another approach is the mixture of experts approach, which involves training a local expert model, which is basically a model trained only on the local data of a client. The FL model and the local expert model are then put into a weighted average ensemble. The next two approaches are augmentations to the fine-tuning approach as well. In the multitask learning approach, we model the problem of personalization as a multitask problem, with the FL training task being one task and the personalization being another. So the objective is to use the model learned from the first task and optimize it for the second task. And this involves altering the loss function. As for knowledge distillation, we treat the FL model as a teacher model and the personalized model as a student model, and this too alters the loss function of the fine-tuning process. As for the combinational approaches, we ended up with 13 combinations of the approaches we mentioned earlier. And this is lesser than 5 factorial or whatever kinds of combinations there can be. And this is because these approaches such as knowledge distillation and multitask learning are mutually exclusive. So they both modify the loss function. And so we can only use them together in the same instance. And fine-tuning and free-space fine-tuning are also mutually exclusive as well. And so we end up with somewhat of an ablation study, which refers to the addition or removal of certain features of a setup to see the impacts on performance. Now, we move over to the result section. We will first see how federated learning models stack up against local models, and how these models are affected by the addition of differential privacy and robust aggregation. Then we see how standalone and combinational approaches impact performance. This is the table of the results that we obtained, but this is quite overwhelming, so we will break it down into bite-sized insights. First, let's talk about how FL models perform compared to local models. For cross-device FL, we can see that for FL models, they vastly outperform the local models, and this shows that FL is definitely a very useful technique in such contexts, which is why it is being used extensively for our next bot prediction task. And also, FL helps these cross-device clients, which usually have very little data, by giving them access to a much greater pool of knowledge. However, for the FL models, so for the cross-silo FL models, the story is not the same. On average, the models underperformed compared to local models for all of the tasks that we explored for cross-silo FL and for all clients. And this is due to the clients having a significant statistical heterogeneity, which prevents the generalized FL model from performing well for each client. And each client already has a significant data set, which lets them train decently performing local models. And such underperformance for FL will disincentivize clients away from using the federated learning process, and this is not desirable, especially for this cross-silo context, since each client contributes a significant proportion of the overall pool of knowledge. And this shows that there definitely must be some way to improve performance to salvage the usefulness of FL in the scenario. When differential privacy and robust aggregation are added in to provide safeguards for privacy and security, the performance declines further as expected. You might notice that for cross-silo FL, there is no differential privacy in the results, and this is because differential privacy is applied on a per-client basis, and ensuring privacy for a small amount of clients, such as in cross-silo FL, degrades the performance beyond recovery. The performance decline from these additions further disincentivizes clients from joining the federated learning process, and further shows how important personalization is to improve performance so that clients will join the federation to make federated learning a viable outcome for usage in the real world. With standalone personalization approaches, we actually added them, the results are very great. And the results show that two of the approaches, fine-tuning and mixture of experts, were able to increase the performance enough to recover from the decline caused by differential privacy and robust aggregation. And they actually outperformed both the original FL model and the local models, which means that they are definitely viable now. And other approaches not mentioned in this slide also show improvements, but they were specific for certain tasks and scenarios. While for fine-tuning and mixture of experts, these two approaches yielded a positive gain in performance for all tasks and scenarios that we explored. As for the combinational approaches, we find that two approaches mentioned earlier, when combined together, give an even greater boost to performance. And this could be due to the combination of fine-tuning and mixture of experts having very great synergy. Fine-tuning will customize the global model, which has been exposed to a lot of different data, to be more suitable towards the local context, while the local expert model that is from mixture of experts will provide a purely local expertise. And so together, the combination covers a much wider feature space than either the local model or the FL model alone, so it is able to perform very well for all sorts of data. As for the other approaches and combinations, we find that free space fine-tuning works as well as fine-tuning for standalone experiments, but they do not work as well when combined with other approaches. For knowledge distillation and multitask learning, we find that they work very well when combined with a mixture of experts, but it's not by themselves. And the best combination that we found in the end that gives the highest average performance across all the tasks and data sets was fine-tuning with mixture of experts and multitask learning. And so in conclusion, we would strongly recommend that personalization should be used for all federated learning implementations in the real world, since it provides a significant boost to performance without much additional overhead. And combinational approaches should always be used instead of individual approaches for personalization. So to summarize, our contributions are as follows. We demonstrated that for certain clients, federated learning does not provide enough performance incentive to be part of the federation, and differential privacy and robust aggregation further reduces that incentive due to performance degradation. We propose combinations of personalization approaches comprising of common approaches, and we've empirically shown that they yield better performance gains than standalone approaches and compensate for the performance degradation. We also observed that certain combinations are more impactful in certain scenarios and tasks, while others improve performance across the board, and a combination of approaches always tend to be better than individual ones. Thank you. So we can now move over to the questions and answers.
Okay, thanks for your presentation. And feel free to raise up any questions you want. And we will have a short Q&A session about 8 minutes. So the floor is open now. Okay, if there is no question for now, we will wait for another 2 minutes. So if during these 2 minutes we won't have any questions, so we will just directly go to the next session. So if anyone has any question related to the topic or about how he can, oh, there's a question. So someone asks, are there any possible improvement in your research?
Well, if you're asking about what further work I can do to improve this, I guess the main thing is that right now, like during this course of my research, it turns out that there's even more approaches out there that has been released since my research was done. So like there are like Monroe envelopes or like clustering that has been done for personalization. So these approaches are also something that are worth exploring. And so we can see even more combinations of different approaches, both new one and old ones, can be combined together. So that's a very possible way forward for it. Yeah. What are the real world applications of your research outcomes? Well, what I would say is that, of course, just now I shared about how FL can be used in the real world, let's say for like the healthcare systems or for your predictive keyboards. But for my specific research outcomes, from what I know, there has been several attempts to use federated learning in the industry for various applications. But what they often come to is that without personalization, the performance is not really desirable, especially because like different companies, different institutions, they have quite a different set of data from each other. So we definitely you need to use personalization to actually make FL viable in the real world. And so essentially like personalization must always be used in these real world applications. Yeah.
Okay, and we'll wait for two other questions and then the Q&A session should be closed. So if there's still anyone who wants to raise a question, please feel free to type it out in the chat box. Okay, there was a question about the federated learning. Maybe you can go back to your slides
Oh yeah,
and
sure.
give a detailed like elaboration.
Yep. Hold on, let me share my screen again. Can you elaborate federated learning clear? Okay. No. Right. So what federated learning is that compared to compared to the machine learning systems that we have now, what machine learning systems will do is that they will have the data, they will send all of this data, or they will send all of the data to the central server, and the central server will then train the model. And then this model is then used by everyone. But for federated learning, what happens is that instead of training the model on a central server, each device, each client will train their own model, and this model is then shared with the server instead of sharing the data. And so that is where the privacy aspect comes in. And so like that's the main difference, and that's the main usefulness of federated learning in our case. Yeah.
Okay, thanks for your elaboration. And okay, is there any other questions? Okay, no, for now. So thanks for presentation and Q&A. And next up, we'll have two more student presentations, one from 2:30 to 3 p.m. and another is 3:30 to 4 p.m. And we also have another guest speaker, Dr. Xu Zhongwen. He will also share with us his ideas, and then we'll have our panel discussion for the day for social unity. So thanks so much for your coming. And if like you won't have any questions to ask, and you can join the next session. Oh, there's one more question from the floor. Any major challenges that you faced during the course of the project? Would you mind like just have
Yeah.
one last elaboration.
All right. So any major challenges? Well, I guess the main challenge was to actually find data sets that can be useful for federated learning, because federated learning is still a rather new thing that we don't really have any suitable benchmarks for, besides like maybe one benchmark for cross-device federated learning. And so what I had to do was to repurpose data sets that have been used for other approaches and then actually make them into the federated learning setting. Like for instance, CIFAR 10 became a cross-device FL data set. And that was essentially the main challenge, to find these data sets there. Yeah.
Okay, thanks for elaboration. And that should be end of this presentation. Thanks so much for everyone's coming.